I would like to share with you the results obtained in collaboration with Marek Winczewski, Leonard Sikorski, Paweł Mazurek, and Mikołaj Czekalewski from University of Gdańsk, and Raja Yeya, and Marek Winczewski and Leonard are here in the audience. So I switched from energetics of computing to energetics of quantum communication. First, let me position where we are. So we are in this intersection of these three domains, like quantum technologies, quantum resources, and quantum thermodynamics. And we are inspired by environmental sciences, and we believe there will be potential applications of the findings. So let's start with quantum resources. As a motivation, I think all know that quantum information theory can be viewed as manipulating quantum resources to achieve some tasks. And this is a list of the resources and tasks you can achieve. So entanglement distribution gives you quantum secure communication, or distributed or delegated quantum computing. Non-locality gives you device independent security. Then gaining purity, you can view this as a work extraction for quantum heat engines. And non-stabilizerness as a enables universal photon quantum computing. So the list is, of course, not finished here. In this context, our goal is to quantify fundamental energy consumption of quantum resource distribution. That's like a broad vision. And by fundamental, I mean this is hardware independent. And as a resource, we focus here on quantum entanglement. So let me briefly recall the definition. A bipartite quantum state is entangled if it's not a mixture of product states, so when it is not separable. And we like, of course, the maximal entangled state, which is an equal superposition of basis states, one for Alice, one for Bob. When they share such a state, we say that they share log to the base to the E bits. And they can process by two local quantum computers and classical communications, which is the set of local operations and classical communication. And the task is of entanglement distribution is just making the parties share the approximately maximal entangled state. That when they share, they can perform quantum teleportation and transfer quantum state to distant location. But then quantum technologies problem comes into play. And there is a challenge, of course, in the real world, noise is inevitable, and for this lecture, I focus on the depolarizing noise. So, for example, if you feed a state into a channel, then it may happen that with probability p, it's preserved, but with probability 1 minus p, it's replaced with a completely noisy state. And there's technological challenge, like how to faithfully transfer quantum bits at large distances via quantum channels, and there is a theoretical solution. You should distribute first noisy entanglement and distill it to pure form and teleport. And if you do it sequentially using entanglement swapping, then you can do it, we believe, at someday we will be able to do it in continental scale, intercontinental scale. So now I want to focus on this distillation of entanglement. A few words about that, because we will try to compute energetics, like how much energy we spend on this procedure. So there are these two parties, Alice and Bob, and they share noisy entangled pairs. And by LOCC, they try to distill something close to, oops. I see here, but oh yeah. I don't know what happened. A maximal entangled state that you try to distill, and roughly the ratio of this, the output log the E bits they distill from divided by the number of copies they invested is the distillable entanglement. An exemplary distillation protocol, actually by Deutsch et al. From PRL, not PRA. In 96 is a bit complicated, so you divide n systems into pairs. For each pair, you perform CNOT gates, you measure the target. When the results are the same, you keep the source. If not, then you trace out both copies. Then you perform Hadamard and then do the same, and repeat until you get high fidelity output. And so all I want you to remember from that is that actually the building blocks. So the building blocks are control NOT gates, measurements, Hadamard gates, and classical communication. And especially we focus regarding energetics, we will take into account just CNOT gates and measurements, and in some way classical communication. We neglect the energetic aspects of single qubit gates. In optics, there are just passive elements and so on. So let's please keep this in mind. And now I pass to the results. Here we are inspired by this environmental sciences in the sense that we want to be resource aware. And the high-level idea is that we want to answer this question: how much energy one needs to spend, to consume, in order to distribute a maximally entangled state via quantum channel and assisted by LOCC operations. So the idea of a quantitative answer is this: that we take a ratio of this energy balance divided by the amount of distributed entanglement. So the energy is the red part is the thing you pay, so you'd pay energy of input state plus energy of distillation process. We subtract the energy of the output state because it's something you got from that, you haven't used it yet. And this is in units joules per EBIT, and you should minimize over the input state, distillation process, and the output dimension. So this is the pictographic view, and by consumption, we mean minimal energy investment to achieve the task of entanglement distribution. Okay, so the first result is the very definition of this like mathematical rigors, and first we approached this in a single shot regime, so we tolerate a fixed error, and so this is single shot energy consumption rate of entanglement distribution as this formula, and then it's a function of a channel, and then we take a non-adaptive many uses of the channel, and we consider asymptotic version. So it's a bit like complicated. I will walk you slowly through this. So let's visualize. You take you consider input states. Half of them you feed into the channel, then and you pay energy of the input. You pay energy of the distillation operation lambda on the output of the channel, which in this case is a choice state of the channel. And then you consider the green part, the output, and there is log the amount of it. So this red part you pay, the green you subtract, and the blue you have in the numerator to see what is the ratio. What's important, like I said, we tolerate epsilon error, and this arrow here is about the infim over all physical realizations. So we are happy to define something that's like by definition uncomputable, because there may be future physical realization of maximal entangled state and in some point. But you can, by this I mean really something that you can prepare in lab that has Hamiltonian description that you can use to compute the numerator, the energies. Okay, and this is this asymptotic version of our non-adaptive channel. So like I said, it's hard to compute this, but to upper bound this quantity, we can pick up a specific platform, and we consider what we call standard energy consumption rate of entanglement distribution, to which we use photons to distribute entanglement. So by standard, there are many more assumptions. So we consider polarized photons without quantum non-demolition measurements, because actually they're more energetically more pricey. And the standard input is just the singlet state, maximal entangled state of dimension the in. And then the energy is just proportional to the number of qubits times 2 h bar omega, given we are in a good regime of a spread of the angular frequency. And the standard distributing channel is that Alice sends half of maximal entangled states to Bob. And the standard output state that we consider here is just entanglement. This is our task. I want to deliver entangled states. If you are interested, what would happen if we go into the waste part that the protocol traces out, please visit the poster by Leonard. There we started this idea of quantum waste management in a software-like manner. So this is the quantity. We replace this blue stuff by fixing a platform of photonic platform. and especially polarization, degree of freedom is important. So now we come into thermodynamics. I have to define what I mean by energy of quantum operation. There were previous approaches by Kiribella, Renato, and Kodors. The warning is like, yes, indeed, you can do this in different ways, actually. So we claim that a good definition should satisfy some axioms, and these are 3 axioms. So energy of performing first lambda 1, then lambda 2 on rho should be upper bounded by energy of performing lambda 1 plus energy of performing lambda 2 on lambda 1. Now, second axiom is locality. So the first is like a subjectivity in time. Second is locality of energy. So this is axiom that follows from the fact that there is no signaling in quantum world. Otherwise, I would notice that Bob switched to a different extension of a quantum of her system. And actually, this is a non-trivial axiom. The third one that concerns really energy, because otherwise the first 2 axioms, just 0 function, also satisfy them. Yeah, so that the energy is lower, or of operation lambda is lower bounded by the balance between input and output energy, output and input in this order. So from these axioms, it follows that, for example, I can upper bound the operation of product type operation by energy of one lab plus the other lab. Yeah. So we model this in the Hamiltonian formalism to know what is heat and work here. So there are 3 systems to consider: a quantum system. You can think this polarized photon, the mesoscopic device that is to do the job, perform the protocol on the system, and the classical control that supplies energy to mesoscopic and device and the system so that it happens. This energy cost is the heat pumped into mesoscopic device and the system, and work performed on the 2 by the classical control. Yeah, that's the definition. Of course, one lambda can be realized by many protocols, so we take infim over that. And then you take energy of a protocol as an integrating over time of a protocol of a drives when we take only one direction from control to the mesoscopic device and the system. I usually say here that we do not like warm coffee by laptop. So we ask like energy, how much laptop, consumes, and yeah, we could do a flow back. Yeah, we could recycle something, but usually we don't do it. So we ask what happens if we don't. So this definition satisfies the axioms which we can use to upper and lower bound the energy consumption rate. Energy cost is a minimal energy needed to perform this lambda. So first, now the results, lower bound. So we focus here on channels that do not increase entanglement. And then once someone could expect, you should pay energy. And this happens. So we have a quantitative result that the lower bound on the standard energy consumption rate is twice h bar omega times fraction log d in over distillable entanglement of the choice state of the channel, minus 1, meaning that if this log d in is strictly more than ed, which happens when there is degradation of entanglement, then this fraction is not 1, so you have non-zero lower bound. You pay energy, and this is the take-home message that irreversibility in entanglement theory implies this quantitative in energy cost in distributing entanglement. Now for upper bounds, we were able to lower bound on the standard energy consumption rate. For upper bounds, we were able to of course, to upper bound the general definition, the energy consumption rate. And we use these axioms and the building blocks I told you about, C0 gates, measurements, and classical communication. We take a specific protocol that realizes C0 gate with probability 1/8, and actually measures 2 auxiliary photons. So we have to answer how much at most you pay, so the upper bound on the energy consumed by measurements, and we use this approach by Riemann-Wolf and co-authors to know that at twice KTLN is an upper bound. And for classical communication, it's disputable. You could do it differently, but we just pay for the making clear register used to transfer classical communication, and then we just lose photons that transfer that. They happen to be classical and disappear. And with that numerics, we got that this depolarizing channel I told you about is just the energy consumption of that is upper bounded by 10 to minus 12 joules per EBIT. And to get this, we neglected the energy of information processing here, like for the classical information processing. And we compared the 3 historically first protocols. So again, I mess up the, sorry. Oops, I'm doing in the wrong direction. So the Bennett et al. Protocol, then the second historically was Deutsch et al. From PRL, again I have back here, and Miguel Ramiro and Dur. And it happened that this Deutsch protocol performs the best in distilling deterministically one entangled state with fidelity 0.9 via the polarizing channel of this that ranges between, here we have just part of it shown. So, and the staircase is because the protocol, like I said, is recurrence. These protocols have many. And instead of summary, I can show you that all the results can be viewed in the plots of joules versus EBIT. So this lower bound, you take numerator to the left here on y-axis, you shift it, and you get the slope of this vector to be the lower bound on standard energy consumption rate. Then you get the same way you can get the upper bound by this Deutsch et al. Protocol. And then the slope of this green vector is some optimal standard energy consumption rate. And we also know that the energy consumption rate is below the red vector because it's something you can achieve. So as an outlook, like a number of problems arise, and yeah, I don't have much time to say about this, but you can study different resources and be more specific. Like we had ideal fidelity of the CNOT gate, for example, but it need not be. So we know it's not in the lab. Okay, and with that, I would like to thank the team. So the bottom list are the corridors, and this group of people that are in Gdańsk. Thank you for your attention.
Thank you.
Oops. These are some rubbish.
Thank you, Karol. Questions, please? Okay. Yeah, first here, green shirt, and then over at the back.
Yeah, a quick question. So regarding your axioms, do they assume zero interaction between A and B, or do you impose them even if there are interactions?
Zero interaction between A and B? You mean for which operations? So for product?
Especially for product, yes.
Yeah, so for product, they assume that, yes, the energy is localized in the sense that if you compute energy here, it's independent of the extension of in what state is the other system in this sense. Yeah? So energy of product is upper bounded by the sum of energies, in particular by the sum of energies of individual actions.
Very good, makes sense. And also, could you quickly comment on the additivity axiom? I mean, what's the rationale behind it?
There was subadditivity actually. So this in time, you mean that it was subadditivity. So that if you compose, then you can have a better way of arranging. I mean, realizing your operation energetically than if you do them first lambda 1 and then lambda 2, because composition gives you it's one lambda that you can decompose in a different way. Yeah. So that's like intuitive. Even like mathematically.
Thank you. Felix, right? I think.
Yeah. Thanks, Karol. Very nice talk. I have a question also about the energy part. Maybe I missed this, but can I think of this as, because you're splitting this up in terms of an external drive and the rest, is this something that looks like splitting it up into something that is equivalent to a unitary type of change and a non-unitary change, or this is a completely different way of thinking about it?
So the splitting was only just that we take the energy that is spent by control to drive what happens on a system and a mesoscopic device. So only this way. So both heat and work that flows in this direction. So like I say, like I said that we could maybe warm a coffee by that or a room or something if we take a heat and work that goes in the other direction, but this is not what usually happens. And we show what happens if you do not recycle the other direction.
Okay, one final quick question while the next speakers prepare. Allez, Federico.
If you're out of question, I always have one. I'm not convinced. I think axiom 1 is well used, but I'm not sure if it's well phrased, but maybe I'm missing something. So if the energy of two operations must be has to be larger than the composed.
It's not sum, it's the composition. So
right?
Yeah, so when you have a so when you first act with lambda and compute energy, and then with lambda 2 and you compute energy on the output of lambda 1, then you're forced to use lambda 1 and lambda 2. Now if you compose them, you may have found cheaper decomposition into lambda 1 prime, lambda 2 prime, so of course it may be cheaper to
I got it.
instead of
Okay, thank you. Let's thank Karol again, please.